When I last left this story, we were in 1752, and the people of Protestant England had grudgingly accepted that Catholics were sometimes right, and adopted their blasphemous calendar. You could argue that the story ends there. After all, the Gregorian calendar is the standard employed worldwide today. But of course, it isn't perfect. No calendar can be. To clarify, the Gregorian calendar produces a year of 365.2425 days, compared to a mean tropical year, as of the year 2000, of 365.242189 days, an excess of about 27 seconds per year. So, nothing simpler, right? Just lop another leap year, sometime around the year 4800. And, roughly a century after England's adoption of the Gregorian reform, that is exactly what the renowned English astronomer John Herschel, son of William, proposed. Specifically, he suggested that any year was a multiple of 4,000, such as, 4,000, be left a common year, just as the Gregorian reform had left most century years. The adjustment would leave a calendar year of 365.24225 days, just 5 seconds longer than the mean tropical year, and thus requiring no adjustment for 17,000 years. There was, however, one slight imponderable Sir John failed to consider. Our calendar does not use the mean tropical year. It uses the time from one March equinox to the next. So, you might be saying, a year's a year, right? Well, because the Earth speeds up and slows down as it orbits the Sun, the length of the year actually varies depending on where you decide to cut it. Our true year, the March equinoctial year, is, as of the year 2000, 365.242374 days, which is just 11 seconds over the calendar year. Herschel's adjustment, if enacted, would render the calendar 11 seconds short, and thus no more accurate than before. So, you might continue in this hypothetical conversation. Can we design a correction for the March equinoctial calendar? Yes, hypothetically. But sadly, not now. You see, the means by which we will measure our future are currently in dispute, and to understand why, we must first go back in time. It's difficult to imagine the rush of feelings that must have overcome their ravaged, broken frames as they saw the towers in the distance. After such loss, such suffering as no voyager till then had undergone, to finally glimpse the gates of home as their last ship rolled over the horizon, loaded with spices richer than gold, yet bereft of food or water, must have been close to divine salvation. Their ordeal had lasted just 2 weeks shy of 3 years. Once they were 5 ships, and 285 men. Now they were 1 ship, and 30 souls, barely clutching to their bodies. They had endured mutiny, shipwreck, and starvation. One of their ships, sent off to chart an unknown land, had simply returned home. Their captain had succumbed to a flurry of swords at the far end of the world. His name was Ferdinand Magellan, and it is by that name that their expedition is usually known, though he never lived to see it completed. The man who did, who conducted the first confirmed circumnavigation of the globe, was named Juan Sebastian Elcano, and as he stepped off the Victoria onto the port of Santiago and the Cape Verde Islands, he and his comrades initially brushed off any platitudes or praise. Refusing offers of food or hospitality, they walked, barefoot, clad in shrouds and carrying candles, to the nearest church to give thanks to God for their deliverance. But there were some among them who wondered if they were worthy of God's grace. According to their journals, the date of their arrival was Wednesday, the 9th of July, 1522. Only, according to their land-loving compatriots, it was Thursday the 10th of July. Had they erred? Crewman Antonio Pigafetta had kept a meticulous diary, as had Francisco Albo, the pilot, and both showed a mismatch of a single day. "How angry must God be with us," cried Pigafetta, "for celebrating his holy days on the wrong days." Thankfully their distress was short-lived, as Gaspare Contarini, a Venetian mathematician and natural philosopher, reassured them they were not at fault. Rather, quote, "having sailed 3 years continually, ever following the sun towards the west, they did greatly lengthen the day." To put that in more modern terms, in circumnavigating the Earth, the Magellan expedition did not simply travel from one location to another and back again. They were sailing a rotating planet, and, just as your speed decreases when you step onto the wrong end of a moving walkway, by sailing against the Earth's rotation, they were slowly losing time to those on land. Eventually, one entire rotation's worth. Conversely, if they had sailed with the Earth's rotation, that is, from west to east, then the Earth would have sped them along by one entire day, and they would have arrived a day ahead of their countrymen. If you found that confusing, I can only say, sorry. It's only going to get weirder from here. The inadvertent time travel experienced by the survivors of the Magellan expedition was an aspect of a much larger problem that would, as the European powers expanded across the globe, result in financial ruin, conflict, and death. For despite the claims of some on this site, the Earth is indeed a globe, and while a globe will happily provide us with absolute coordinates for north and south, what we call latitude, any coordinates for east and west, or longitude, would always be completely arbitrary. While latitude could be measured simply by calculating the sun's altitude in the sky, longitude could only be determined by observing specific astronomical events, such as lunar eclipses, and comparing the timing of their occurrence to observation at another location. The difference in timing could then be converted into longitude. Needless to say, this method was all but useless at sea, where not only was one unlikely to have a lunar eclipse to hand, but the unsteady motion of a boat made precise astronomical observations next to impossible. This was no trifling issue. Even a slight delay of a few days or weeks could lead to death by scurvy. Numerous shipwrecks and failed voyages could be traced solely to misread longitude. Captains often compensated by keeping their ships in sight of land, which left them prey for pirates. The simplest solution was always for a clock to be placed on board ships to tell the time at a fixed point, say the point of departure, and then calculate the difference from local noon. For every hour's time difference, 15 degrees of longitude. The problem was that the most accurate clocks required a pendulum, and a pendulum can only function if it was swung from a fixed motionless support. Impossible at sea. Christian Huygens, the inventor of the pendulum clock and a frequent visitor to this channel, tried his hand at the problem in the 17th century, even seeing some success in the relatively still Mediterranean, but failing outright on the wild main of the Atlantic. His attempt at a mainspring-powered clock, the same technology that powers wrist and pocket watches, came to ground after he couldn't account for the effects of temperature and humidity. Another individual who has made multiple appearances on my channel is Sir John Flamsteed, the first astronomer royal. Born in 1646 to solid middle-class stock in the north of England, from childhood Flamsteed suffered from, stop me if you've heard this before, chronic ill health. In 1669 he sent an ephemeris to the President of the Royal Society, who put him in touch with Jonas Moore, astronomer, mathematician, and Surveyor General of the Ordnance, who gifted Flamsteed one of the first micrometers, a device for tracking minute changes through a telescope. After attaining his M.A. at Cambridge, where he met Newton, he made another common choice for those of his vocation, and took holy orders. Fate, or rather Jonas Moore, had other ideas. In 1674, Charles II's French mistress persuaded him to hear the proposal of a man known only as Mr. Saint-Pierre, to use the moon to calculate longitude at sea by timing the passage of stars behind it as they move through the night. If the name wasn't enough of a giveaway, the plan was unworkable, which Flamsteed, called by Moore to consider the matter, asserted, since neither lunar timetables nor the knowledge of the locations of the stars were nearly precise enough. Jonas Moore had been pressuring Charles II for the establishment of a royal observatory. Flamsteed's argument clinched it. On the 4th of March 1675, Flamsteed was made the King's Astronomical Observator, with an allowance of £100 a year. His remit was, to quote Jonas Moore, forthwith to apply himself with the most exact care and diligence to the rectifying of the tables of the motions of the heavens and the places of the fixed stars, so as to find out the so much desired longitude of places for the perfecting of the art of navigation. 4 months later, construction began on the new Royal Observatory on the hill at Greenwich Park, the choice of its designer, Christopher Wren. No one knows who first coined the term astronomer royal. It's possible Flamsteed adopted it himself. That £100 would have to stretch, as Flamsteed ran into that perennial problem of royally backed astronomers, lack of money and support. Once ensconced in the Royal Observatory, he had to spend thousands of pounds of his own money to purchase the necessary equipment. This meant that his star catalogue, updated with the latest telescopic observations, were perennially late, which led to a lifelong, bitter feud between Flamsteed and his former friends Edmund Halley and Isaac Newton, who required them for their researches. It even got to the point that Halley stole Flamsteed's work and published it without his approval, a grievous, if understandable, transgression. Flamsteed died in 1719, 6 years before the final volume of his catalogue was published, but nonetheless having succeeded in his duty. His star catalogue was accurate to within seconds of arc. Even the legendary catalogue of Tycho Brahe, still widely used at the time, was only accurate to within 2 minutes of arc. This was accurate enough to allow for determination of longitude by lunar observation. It was in these star catalogues that Flamsteed made the innovation for which he is best remembered today: Flamsteed designations. 75 years earlier, the German astronomer Johann Bayer had established the convention of naming stars in order of brightness according to the Greek alphabet, followed by a Latin genitive, most famous today in stars such as Alpha Centauri and Tau Ceti. But Flamsteed's catalogue, with the addition of the telescope, required a step beyond omega, and replaced the Greek letters with Arabic numerals. It also ditched the imprecise brightness criterion and simply numbered the stars from left to right. The most famous stars known by their Flamsteed designations today are 61 Cygni, the first star to have its parallax measured, 51 Pegasi, the first sun-like star found to host an exoplanet, and 34 Tauri, a star Flamsteed recorded several times, later revealed to be the planet Uranus. Calculations of longitude via lunar distance, or lunars as they were called, would soon become the standard method for navigation. The legendary James Cook employed them to great effect in his Pacific voyages in the late 18th century. But while they were more practical than lunar eclipses, they were still prone to error. For one thing, even the best 19th century sextants were only accurate to within 30 seconds of arc. For another, because the size of the moon in the sky varied over time, the almanacs used to record the timings of star passages had to be set to the center of the moon, with daily listings for the moon's diameter. Also, every observation had to be calibrated for the effects of parallax and atmospheric distortion. And of course, if the sky was cloudy or the moon was new, no observations could be made. Finally, the required observations were difficult. In a fleet of East India merchant ships, perhaps 10 people could navigate by lunars. For a rising naval power like Britain, accuracy was vital, and in 1714 they resolved to do something about it. On the 8th of July, the British Parliament passed an act allowing for a longitude prize. £10,000 if a method for determining longitude at sea could be shown to work within a 60-mile error after a 6-week voyage. £15,000 for a 40-mile error, £20,000 for 20 miles. For perspective, 60 miles, or 100 kilometers, is about 2/3 the length of the Suez Canal. That was considered a desirable margin. The longitude prize was not the first of its kind, but it was the largest and, ultimately, the only one to ever be paid out. the committee was duly flooded by the mental excretions of every crackpot and crank in the kingdom, offering solutions as diverse as sundials, sea windmills, and even squaring the circle, which would be difficult to tie to longitude even if it weren't a mathematical impossibility. One might expect the eventual recipient of the award, John Harrison, to be an intellectual luminary in the mold of Christian Huygens. And he was, after a fashion. But as the son of a carpenter who had educated himself in the repair and construction of clocks, he was not the kind of philosophical theoretician that was the stereotype of scientists of the time. He was a builder, not an explainer, a fact that may have worked against him. By 1730, and the age of 37, Harrison felt he had the ideal concept to win. Cannily, he made his first appeal for recognition, a plan for a temperature-resistant pendulum called the gridiron, and a near-frictionless escapement called the grasshopper, not to the prize committee, but to Edmund Halley, who had succeeded Flamsteed as Astronomer Royal. Halley bluntly informed Harrison that the prize committee would not advance him a shilling, and that if he was in need of funds he should take his plans to the respected clockmaker John Graham. Graham advanced Harrison the money he needed for the project, and Harrison got to work. The first model took 6 years to build. It compensated for motion at sea by using 2 interconnected swinging balances instead of a single pendulum, and for changes in temperature by the use of near-frictionless materials, such as oily wood and polished brass. After testing it on the River Humber, Harrison took it before the board. The clock was tested at sea on a journey to Lisbon and found to be more accurate than dead reckoning. The return trip even met the 60-mile accuracy minimum. While this was not the 6-week voyage demanded by the committee, they were impressed enough to grant Harrison £500 for further development. His second chronometer was essentially a stronger, more robust version of the first. However, Harrison realized that the twin balances could not adjust for yaw, and with the permission of the board and a further £500, he decided to abandon it for a circular balance. This third chronometer, begun in 1740, took him 19 years to build and adjust. But it too did not function as Harrison desired, as he did not understand the physics behind the springs used to power it. His final chronometer, a mainspring-powered, watch-like creation, bore little resemblance to the golden clockwork palaces of his previous attempts, and was intended to serve merely as a backup, in case, as he feared, his third chronometer underwhelmed. To his shock, the chronometer outperformed its predecessor. Unlike watches of the time, which were accurate to just a minute per day, Harrison's watch possessed an outsized balance wheel, which allowed it to tick 5 times a second, and increased its accuracy exponentially. In 1761, Harrison, or rather his son William, the guy was pushing 70, put the watch to the test on a journey to Jamaica. After 9 days out of sight of land, the captain insisted via dead reckoning that their longitude was 13 degrees. Harrison argued it was 15 degrees, and was proven correct when the island of Madeira appeared over the horizon the next day, much to the joy of the crew as they were, quote, in want of beer. Upon reaching Jamaica, the crew found that Harrison's watch had guided them to port to an accuracy of 1 mile. Not 60. Not 20. 1. That's it, then. Britannia rule the waves, scatter her enemies, and make them fall. Except, no. The committee insisted on a second trial run, as the longitude of Jamaica, they argued, was not known precisely enough. They were generous enough to grant Harrison £2,500, an eighth of the total, on account. The second trial, to Barbados, took place in 1764, under the supervision of Neville Magellan, soon to succeed Halley as Astronomer Royal. The watch guided them to Barbados with an accuracy of 10 miles. Not as spectacular as the previous result, but still worthy of the richest prize. Actually, somewhat reasonably, the committee demanded that Harrison construct 2 more clocks, to be independently tested by disinterested parties, and begrudgingly advanced him £7,500, meaning he now had half of what he was owed. The duplicate went with James Cook on his journey to the Antarctic. Despite Cook singing its praises, Neville Magellan, who had developed a distaste for both timepieces and Harrison, managed to conclude, against all available evidence that Harrison's watch was not fit for purpose. Thankfully, Harrison eventually found the ideal patron, a still sane George III, who proclaimed, "By God, Harrison, I will see you right it." You'd think that would be enough, but the old days of royal absolutism were over, and Harrison still had to petition Parliament. Under threat of investigation, the committee buckled and finally handed Harrison all he had so richly earned. Except, no. Even though under the terms of the prize, any and all chronometers constructed as part of a winning trial became property of the state, the committee insisted to Harrison that the £1,260 they had given him to construct said chronometers was now a loan. Harrison lost both the money and the timekeepers, but was doubtless relieved. Harrison's watch had one crippling flaw. It was expensive, with units topping at £450 apiece. But Britain could hardly call itself the cradle of the Industrial Revolution if it couldn't find ways to manufacture goods at scale. And soon, new generations of clock and watchmakers were simplifying the design. And here is where John Harrison inadvertently redefined time. So accurate was his chronometer that not only did the British Navy become the most powerful military in the world, it would also produce the most accurate and dependable hydrographic maps and charts in common use, which would become the standard for the majority of seafaring nations. Because these charts, as to be expected, employed the Royal Observatory at Greenwich as their prime meridian, so those nations followed suit. Not all of them, obviously. The road to my city's eventual crowning as the center of the world took the better part of a century to traverse, and the obstacles were many. Prime meridians are, of course, arbitrary. There is no center to the surface of the world. If you started out your door today and kept walking, sailing, or dog-sledding in a straight line, you would eventually arrive back where you started, regardless of the direction you chose. In a sense, from our perspective, the surface of the Earth is infinite. The need to mark out a boundary line for the known world was obvious even to the earliest cartographers. Ptolemy, in his Geographica, chose the Isles of the Blessed, the paradisiacal home of the Greek heroes, as his prime meridian, believed to lie in the Atlantic Ocean, beyond the Pillars of Hercules, or Straits of Gibraltar, corresponding to Hierro, or Pharaoh, in the Canary Islands. This was adopted by scholars throughout the Middle Ages, and, as it did not pass through any nations, except Iceland, it was employed as a convenient meridian even into the early modern period. And for Edward Gibbon, author of The Decline and Fall of the Roman Empire, that was enough. As he complained in 1789, the perfect Pharaoh meridian had been thrown to the dogs of nationalistic pride, with every naval power asserting that the world began with them. Quote, "The absurd vanity of the Spaniards and the Dutch, the French and the English, has variously transported this ideal line from a common and familiar term. The longitudes of Madrid and Amsterdam, of Paris and Greenwich, must now be compared, and the national diversity of speech and measure is aggravated by a new source of perplexity and confusion." Unquote. To give an example, the Spanish measured their empire westward of Cadiz, while the Portuguese counted theirs east of Lisbon. Cadiz and Lisbon are less than 3 minutes apart in time. Manila, the farthest westward extent of the Spanish Empire, and Macau, the farthest eastward extent of the Portuguese, are about 30 minutes apart. Yet these colonies' respective noons were separated by 23 hours. This day difference caused issues for navigation, since almanacs determined latitude by the sun's position on specific days. Gerardus Mercator, of the map projection, placed the Cape Verde Islands as his prime meridian, on the assumption that compass needles there pointed true north. As it happens, the so-called agonic meridian is not fixed, but varies according to the strength of Earth's magnetic field. Globes in the years between 1500 and 1700 varied their meridians between the Canaries, the Cape Verdes, or the recently discovered Azores, with little regard for consistency. In 1724, Louis Fouille traveled to Pharaoh to determine the prime meridian, the first geodetic mission to do so, and determined Pharaoh's longitude as 19 degrees 55 minutes west of Paris, though 20 degrees was settled on, which allowed Paris to become the standard French meridian. By the 1860s, 14 different base meridians were in common use, with little consistency even within countries. Spain used Cadiz, Tenerife, and Paris, while Russia used Paris, Greenwich, and Faro, as well as Estonia, considered the empire's western edge. The recently born United States initially settled on its first capital, Philadelphia, as its prime meridian, while in 1804 Thomas Jefferson tentatively declared the White House the prime meridian. The decision met with much opposition, as many argue that Greenwich was more practical. As America expanded westward, however, that practicality waned. Eventually, a compromise was reached. Navigators could continue to use Greenwich as they were accustomed, while a separate Washington, D.C. meridian would be employed for domestic geography and astronomy. Many in America thought that a single, universally agreed meridian was only a matter of time. Others considered the ideal wishful thinking. As one Harvard professor lamented, quote, "There is no reason to think that one single first meridian can ever be established with the common consent of nations. All desire it, but how many will agree on the choice?" But the need was growing. The adoption of the metric system by science led to a push for a common meridian, which naturally gravitated toward Greenwich. Apart from its ubiquity, another advantage of Greenwich was that, while it did bisect several major landmasses, its antimeridian, what we now call the International Date Line, did not. Also, the relative closeness of London and Paris, just 2 degrees, made their meridians easy to confuse. In 1871, the first ever International Geographical Congress voted that the Greenwich meridian should be universally adopted, though they lacked the authority to enforce the decision. The idea was challenged by France, in the person of naval engineer Adrien Germain, who argued that there was no need for a single meridian, that the dangers were exaggerated, and that the universal code of signals already in use included the code, "What is your initial meridian?" Germain also argued that the French almanac, the Connaissance, had undergone sufficient improvement to be the peer of the UK's world-conquering edition. This, even though Urbain Le Verrier, head of the Paris Observatory and discoverer of Neptune, had disallowed his staff the use of French maps due to their unreliability. In 1874, the Congress met again, and, despite Germain's attempts to exclude the topic from discussion, again broached the meridian. As I am sure many of you know, the systemization of time began with the rise of the train. While your typical village could run perfectly fine with a noon a few minutes after a village 20 kilometers away, if trains kept to local times, the results would be catastrophic. In 1840, the Great Western Railway, which ran between London, the South West, the Midlands, and Wales, adopted a single time across its network, based on Greenwich. Others soon followed, creating a standard railway time. In 1852, time signals were first sent by telegraph from the Royal Observatory, allowing clocks around the country to be synchronized. By 1855, 98% of clocks in Britain were using Greenwich time. But Greenwich Mean Time, GMT, did not become the standard for the entire country until 1880. The idea of dividing the world into 24-hour-sized zones was conceived by Sandford Fleming, a Scots-Canadian railway engineer. According to legend, in 1876 he was stranded for a day in a village in rural Ireland when a faulty guidebook caused him to miss a train. This story seems unlikely, as railway engineers are generally aware of local train times. Fleming had initially considered the possibility of setting every clock in the world to the same universal time, regardless of the time of day, with personal chronometers set to local time. Thus, one could run one's personal affairs by local time, but when precision was required, such as with trains, deal in absolute time. He later amended the idea to 24 individual time zones, with Greenwich as the prime meridian. In 1879, his proposal was taken up by the British government, who forwarded it to 18 other nations. That same year, American Cleveland Abbey, who 2 years previously had been frustrated by being unable to time the occurrence of an aurora because half the reporting observers had used local time and half had used railway time, released a similar report for the American Astronomical Society. He then presented his idea to the International Geographical Congress during their third meeting in 1881. After years of vacillation, in 1881 the Congress declared that they would reach their final decision at their next meeting. The International Meridian Conference, with a stated goal, quote, to adopt a single prime meridian for all nations in place of the multiplicity of initial meridians which now exist, was held in Washington, D.C. on the 1st of October, 1884. President Arthur asked Congress for $10,000 in funding. He got 5. As a result, the delegates had to pay their own expenses. 25 countries attended the conference, a sizable portion of the total in 1884, though China was conspicuously absent. Among the delegates sent were Fleming, representing Canada, and John Couch Adams, the British protagonist of the search for Neptune. Russia, of course, sent a Struve. To read the newspaper reports of the event is to be astonished that any agreement was reached at all. The Times reported the Americans had described the French as puerile, while the journal Science complained that, quote, the time has been mostly taken up with political diplomacy and sentiment. The French demanded the meridian be neutral, not passing through any continent, and the geography offered only 2 possibilities, the Azores or the Bering Strait. Simon Newcomb, the astronomer who would eventually conduct the famed Michelson-Morley experiment into the speed of light, argued that there was no such thing as a neutral meridian, as any choice would have to be referred to a national observatory. France's objection was defeated 21-3, with only Haiti, a former French colony, and Brazil voting with them. Fleming argued that, as most tonnage used the Greenwich meridian, the antipode to Greenwich, which passed only through a few Pacific islands, made a good neutral compromise. He was ignored. American delegate Lewis Rutherford proposed a vote on a resolution declaring Greenwich, specifically the line passing through the Airy Transit Circle telescope at the Royal Observatory, the meridian. But the French delegates declared him out of order, citing tradition and the expense of changing all their charts. The other delegates suggested, to soothe French egos, that if they accepted the Greenwich meridian, they would encourage the US and the UK to adopt the metric system. You can guess how well that encouragement worked. The French were again defeated 21-3, with just Haiti and Brazil siding with them, though this time they abstained. The next decision was whether the meridians be counted a full 360 degrees, or 180 degrees east and 180 degrees west. Most European countries preferred the former, though the non-Europeans swung the vote, and the latter won. The third decision, to adopt a universal day, was passed 23-2. The final and most controversial vote, to begin the civil day at midnight at Greenwich, passed 14-3, with a whopping 7 abstentions. The controversy was largely down to astronomers, who for centuries had had their own cozy arrangement with time. Their days began and ended at noon, to avoid confusion during the starry hours. The long trek to scrap the astronomical day is outside the scope of this story, but suffice to say it was gone by 1925. If we were to judge the conference by its immediate effect, then it was a failure. The decrees were only advisory, and the decision to adopt the prime meridian stalled in the U.S. Congress. If the very hosts of the conference couldn't abide by its rulings, then why should anyone else? Japan was the only country to implement the recommendations, but solely for navigation. France made no change whatsoever. By 1898, 14 separate prime meridians were still in use. But, slowly and surely, the train crushed all before it. Continental Europe slowly gave in to the convenience of having a single shared train time. Germany and Austria agreed to shift their meridians from their respective capitals to Greenwich +1, while the Balkans shifted to Greenwich +2. The British Empire, which covered a quarter of the world's land surface, eventually established a Greenwich-based time system. By 1891, France had adopted Paris time. Oddly, this meant that its trains, which had been on Paris time for years, were now out of sync, because the clocks at railway stations were deliberately set 5 minutes fast to stop passengers arriving late. As the railways were in private hands, this discrepancy remained. But one invention would ensure the dominion of Greenwich time forever. In our Wi-Fi-wrapped world, it can be difficult to understand what a revolution the first wireless communication, what we quaintly call radio, was when it premiered. With the addition of a radio tower, information could be sent literally anywhere at the speed of light, including to moving ships. Until then, the idea of using time zones on the ocean was seen as redundant. Eventually, it would become vital. Once the French placed a radio transmitter on the Eiffel Tower, it was over. In 1911, they begrudgingly switched to Greenwich time, though they referred to it as Paris time minus 9 minutes and 21 seconds. By 1913, the Greenwich meridian had been adopted by all nations. Also, the rise in instantaneous communication accelerated the need for the adoption of a universal time. Today, Greenwich Mean Time, or GMT, is the standard time for military operations, space missions, air traffic control, and polar stations. While it would eventually be superseded as the Universal Civic Time, after a fashion, for reasons we shall see later, it remains the center of the world for navigation. The adoption of Greenwich as the prime meridian did leave one large tangle. What to do at the other side of the world? One of the reasons for choosing Greenwich as zero longitude was that its antipode, 180 degrees longitude, was in the middle of the Pacific, and so did not inconvenience any large populations. The populations it did inconvenience, however, it inconvenienced hard. Today, we call the opposing meridian to Greenwich the international dateline, and it is literally where the Magellan dilemma plays out at the speed of modern life. If it is 1 p.m. on Monday at Greenwich, then by definition, 12 hours west of Greenwich, it is 1 a.m. on Monday, while 12 hours east, it is 1 a.m. on Tuesday. Crossing the international dateline doesn't just shift you into the next or previous day. It propels you forward or backward an entire 24 hours. Magellan's crew lost a single day on a 3-year voyage. Today, it is possible to cross the Pacific on a plane and arrive before you left. An inevitable consequence of attempting to map linear time onto a circular world. And so we arrive at the unfortunate archipelago of Kiribati. Kiribati, yes, that is how you pronounce it, is a far-flung speckle of Pacific islands and coral atolls scattered across 35 degrees of longitude, roughly the distance from Portugal to Ukraine, yet comprising less than 1,000 square kilometers of land, much of it uninhabited. Because it straddles not only the equator but also the Greenwich antipode, it is the only land that could justifiably describe itself as the center of the world. Yet its locale, despite the cachet, was far from des res. Imagine trying to keep an appointment, let alone run a business, when half your country was 24 hours ahead or behind the other. By 1995, the people of Kiribati had had enough, and moved their section of the international dateline 2 hours east. Since there is no legally binding definition of the international dateline, there wasn't much anyone could do about it. This ruling created an astonishing loop in time. The Line Islands, the farthest of the Kiribati Islands, see the same dawn as Hawaii, Tahiti, and the Aleutian Islands. Yet for the Line Islands, that dawn lies 24 hours in the future. When flying northward across the Pacific, it is literally possible to fly over tomorrow. A few years later, with the arrival of the millennium, the people of Kiribati suddenly realized they had a potential tourist draw. They briefly rechristened their easternmost atoll, Caroline Island, Millennium Island, and marketed it as the first place to see the millennium in the world. When the day finally dawned, a team of dozens of journalists flew the several hours to Caroline Island to mark the first dawn of the new age, to an estimated worldwide audience of 1 billion, much to the chagrin of the more traditionally aligned Pacific Islands, who felt their oceanic cousins had jumped the queue. With that, you could argue that, at least for now, the new year has been fixed, not only in time, but also in space. A person standing on Caroline Island will see the new year break as close to the precise moment as possible. But, of course, it could never be that simple. In 1927, an invention emerged that, like the shipping container, the sewing machine, or indeed the Greenwich meridian, managed to utterly change the world without anyone really noticing. And it emerged from one of the most mundane substances on Earth. Quartz is crystalline silica, essentially oversized sand. Silica is the commonest compound in the Earth's crust. To call it common as dirt would be to insult dirt. But it has one remarkable property. It is piezoelectric, meaning that applying pressure to it produces an electrical current. When struck, it rings like a bell, which then produces an electrical current of the same frequency. This current can then be translated into a precise count of the vibration. The exact frequency is dependent on the cut and size of the crystal, but the most common is 32,768 cycles per second, the 15th power of 2, making it easy to divide and count. It is staggering to comprehend what a hyper-accurate clock made from bespoke sand did to the world. If you are watching me on your smartphone, that phone has a quartz oscillator. If you're watching me on a computer, that computer has a quartz oscillator. If you are masochistic enough to own an alarm clock, that clock has a quartz oscillator. If you're driving your car, you are surrounded by 100 quartz oscillators, from the timing of the windshield wipers to the communication with your GPS. If an electronic appliance requires timing in any way, it almost certainly has a quartz oscillator in it somewhere. That's today. In 1927, the quartz oscillator opened the door to a new understanding of time. By 1927, time was seemingly fixed throughout the world, with even the laggard Russians going Gregorian in 1923. But there remained one final problem. Exactly what time was it? No, really. You could be standing on the tip of Caroline Island with your quartz clock telling you it was exactly midnight. But how could you be sure it was truly the new year? Exactly when does that 32,768th cycle finally end? And is that even a precise enough count? For as long as we have ordered time, we have relied on 3 markers to aid us: the cycle of the day, the passing of the year, and the change of the moon. But as our man-made chronometer's precision increased, it gradually became clear that nature's clocks were faulty. It was already known by then that the rotation of the Earth was more than a mere spin. In 1695, in another of his archaeoastronomical masterstrokes, Edmund Halley noted, by examining the timing of ancient eclipses, that the moon had to be revolving more rapidly today than in ancient times. Attempts to answer this anomaly lasted hundreds of years, until in the 1860s it was finally understood. The moon wasn't getting any faster. Earth's rotation was slowing. The gravity of the moon, as everyone knows, pulls on the oceans, creating the tide. Friction from the ocean's motion across the seabed dissipates energy, sending the moon farther outward and slowing the Earth's rotation. As a result, the length of the day increases by an average of 2.3 milliseconds per century. Additionally, rebound of the Earth's crust after the Ice Age, by making the Earth slightly more spherical, has shortened the day by 0.6 milliseconds per century. Tidal drag, while certainly an issue in the long term, as we shall see, was negligible for everyday timekeeping. But other motions were not. In 1891, American astronomer Seth Carlo Chandler discovered that, in addition to the 26,000-year wobble in the Earth's rotation known as the precession of the equinoxes, there was an additional 9-meter wobble that took place over the course of 428 days, likely caused by motions within the Earth's molten core. With the advent of quartz clocks, even subtler motions were found. The Earth's rotation varies randomly over the course of decades by as much as 4 milliseconds, likely due to flows and eddies in its liquid outer core. It was also found to increase in summer and decrease in winter, a few milliseconds each way. Astoundingly, this is almost certainly due to changes in atmospheric circulation over the course of the year, as wind blowing against mountains slows rotation down. In 1983, the Earth's rotation slowed by a few milliseconds in the lead-up to El Niño. For millennia, the second, the foundation of timekeeping, have been defined simply as 1/60th of 1/60th of 1/24th of a day. But if the day could no longer be precisely measured, that was no longer feasible. And in 1927, astronomer André Danjon proposed that if the second could not be defined as the fraction of a day, then it must be defined as the fraction of a year. In 1950, Gerard Clements of the U.S. Naval Observatory suggested that time be defined by the location of the sun in the sky against those of the other planets, so-called ephemeris time. In 1952, the proposal was adopted by the International Astronomical Union, and in 1956, the second was officially defined as 131,556,925.9747 of the tropical year 1900 as measured from midnight GMT on the 31st of December 1899 ephemeris time. This definition would last all of 11 years. A new means of measuring time, one entirely independent of the sky, was slowly flanking the IAU, a means which, a century earlier, was not even theoretical. Atomic theory, the idea that matter could be reduced to discrete essential particles, is as old as the ancient Greeks, and by the 19th century, the budding science of chemistry had shown that elements combine in specific ratios, suggesting they were composed of finite particles. But the idea that those particles could themselves be composed of particles, the fabled electron, neutron, and proton, would only come into focus at the start of the 20th century. We now know that the reason red objects are red and blue objects are blue is that they absorb white light, which contains all colors, at all save certain frequencies, which they re-emit. These frequencies are as individual to specific materials as a fingerprint, and are used by astronomers the world over to identify chemical compounds in space. A quartz oscillator, as I noted, usually cycles about 33,000 times per second. Waves of red light typically cycle at 430 quadrillion times per second, while blue light cycles at 670 quadrillion. In 1879, before subatomic particles were a twinkle in Ernest Rutherford's eye, William Thomson, 1st Baron Kelvin, for whom the temperature scale was named, speculated that these frequencies, if harnessed, could make the ultimate clock. Most people are familiar with the high school image of the atom, a core of protons and neutrons orbited by a swarm of firefly-like electrons. Electrons are not a random flock, but arranged in a precise order. The first layer, called a shell or energy level, has room for 2 electrons, with the third then taking up the shell above. The second has room for 8 electrons. The third has room for 18, the fourth 32, and so on. The reason that red and blue objects appear red or blue is because the electrons within their atoms absorb white light, which causes them to jump one level. Then, when they return to their original state, they emit a photon of light at the energy level's precise frequency. The simplest example of this is hydrogen, which possesses only 1 electron, except that light emitted by hydrogen cycles at 100 quadrillion times per second, not a number easily counted. And from here I'm afraid you're just going to have to trust me because we're going quantum. Both the electron and the proton have a dipole, which shifts depending on the orientation of the electron. Because protons are positively charged and electrons are negatively charged, if the poles are aligned, the charges repel, and the electron moves up. If they aren't, the charges attract, and the electron moves down. This shift is known as the hyperfine state for the ground state, and for hydrogen occurs at a fairly measly 1.42 billion cycles per second, a number far more easily measured. But perhaps too measly? Yeah, it's nice to be able to count it, but you need some extra cycles in there for precision. Thankfully, there's a whole group of elements that, like hydrogen, also have 1 electron in their outer energy level. They're called the alkali metals, and they are wild. They can't exist on their own in nature and instantly explosively react with pretty much anything they're exposed to. The stars of the alkali metals are lithium, sodium, and potassium, but the horse for this course had to be cesium. Cesium has a number of unique properties that make it ideal for an atomic clock. Rather surprisingly, it is the largest atom in the periodic table, despite being only number 55. The reason for this is that while increasing the number of electron shells does increase an atom's overall size, increasing the number of protons actually decreases it, since protons, being positively charged, attract the outer electrons and bring them closer to the nucleus. Since adding protons is what changes one element to another, heavier elements than cesium all have more protons, and thus tighter electron shells. Cesium's size means its outer electron is very weakly bound, making it easy to excite. Another exploitable property of cesium is that it has only one naturally occurring isotope. For the uninitiated, an isotope of an element is a variation that contains the same number of protons, but a different number of neutrons. It's a bit like playing Jenga. Pile on or take away too many neutrons, and the atom falls apart. When it does, it releases bullets of subatomic particles and high-energy light that we call radiation. The more unstable an element is, the more radioactive it is, and the less likely it is to survive. But some elements possess isotopes that, while not exactly stable, are stable enough to hang around. Carbon-12, the most stable form of carbon, and carbon-14, its less stable cousin, are perhaps the most familiar examples, but many elements appear in mixtures of common and less common isotopes. Since cesium has only one isotope, cesium-133, we can ensure that every atom we read will be exactly the same. The hyperfine transitions of the first column elements all release radiation in the microwave spectrum. Hydrogen's hyperfine transition frequency, 21 centimeters, has become a beacon in radio astronomy, as it can be used to track the motion of hydrogen through the galaxy, and thus the motion of the galaxy itself. Cesium operates at the 3.26 centimeter line, corresponding to about 9.2 billion cycles per second. Shorter, but still well within the microwave range. As it happens, this is also the range in which radar functions, and happily there were plenty of excess radar sets left over from World War II. And in 1955, at the National Physical Laboratory in the UK, the first successful cesium atomic clock ticked for the first time. The National Physical Laboratory measured the spin-flip frequency of the cesium atom at 9,192,631,830 plus or minus 10 cycles per mean solar second. No other quantity had ever been measured so accurately. It was clear that atomic clocks were now the future. To obtain a value so precise using ephemeris time would require 4 years of lunar observation. Sneakily, the atomic clock was originally sold as a means to tell accurate ephemeris time, rather than replace it. But the writing was on the proverbial wall. When it came to who owned time, the French had lost the battle, but they had not lost the war. They had one unbeatable card. They invented the metric system, and when the metric system was adopted by international science as standard, that meant they controlled the very nature of how science measures time itself. In 1960, the International Bureau of Weights and Measures, the Bureau International des Poids et Mesures, decreed the second as defined by ephemeris time, a standard international unit of measure for a fundamental quantity. As a result, a group of laboratories and observatories agreed to a successor to Greenwich Mean Time, Universal Coordinated Time, basically GMT without the additional Englishness, abbreviated to UTC, a compromise between CUT, Coordinated Universal Time, and TUC, Temps Universel Coordonné, because apparently the 1,000-year Anglo-Gallic War must be waged even over acronyms. Today, that coordination is done by 49 separate cesium clocks, checked against each other by GPS satellites. All are expected to be within 1,000 to 100 nanoseconds of UTC as calculated by VIPM. Very few are as accurate as 100. If a clock is found to be outside the acceptable limits, then it must be slowly steered back, a process that takes weeks. In the 1980s, errors could amount to microseconds. Today, they are in tens of nanoseconds. You might cry indolence, but in fact it is physically impossible for two clocks to tell the exact same time. Even ignoring the effects of temperature, air pressure, or the simple presence of people, Einstein showed that time is relative to one's position, and slows down the faster you travel. Two cesium clocks flown around the world in different directions will, purely due to their speed, show differences in time in tenths of microseconds. Einstein also showed that gravity and acceleration are equivalent, and because the strength of gravity increases with proximity to the center, time actually moves more slowly at your feet than at your head. Atomic clocks must be recalibrated by 109 parts per quadrillion for every kilometer above sea level. Gravity even varies with the density of material, so our hypothetical harbinger of the new year, standing on the edge of Caroline Island, would experience a different time if she were standing on sand than on stone. Finally, in October 1967, the General Conference on Weights and Measures defined a second as the duration of 9,192,631,770 cycles of the radiation corresponding to the transition between the two hyperfine levels of the ground state of the cesium-133 atom. Ephemeris time proved to be ephemeral. Today, with mass finally defined by Planck's constant, the second is now the one measurement from which all other standard units are derived. You'd think this made things simpler, but instead, humanity suddenly had to grapple with having two different definitions of time. Temps atomique international, or TAI, represented the endless plodding tick of the cesium atom on into eternity. UTC is the old Greenwich time, based on the rotation of the Earth. Yeah, that. Remember when I said we'd be getting back to tidal drag? The atomic second, the invariable, invincible, and indomitable tick upon tick, heedless of the universe around it, is based on the ephemeris second, the length of a second in the year 1900, when the moon was 20 centimeters closer and the Earth span 1.5 milliseconds faster. Okay, you might think. Just add another second every 500 days. Problem solved. Except, no. Remember all those random shifts in the Earth's rotation speed? The ones no one can predict? Well, they have to be accounted for. And the International Earth Rotation and Reference System Service, yes, that is a thing, does that, mind-blowingly, by calibrating signals from quasars billions of light years away, captured by radio telescopes thousands of kilometers apart. The orientation of the telescope, and thus the Earth, can be measured to the milliarcsecond, the sort of precision used to detect extrasolar planets. The IERS then votes on whether they should add a new leap second. Since the leap second was introduced in 1972, they have done so 22 times, usually at the ends of December or June. And so, after more than 2,000 years, we have come full circle. Our calendar, as in ancient Rome, is controlled by a largely unaccountable, anonymous elite who dictate the lengths of our days and years according to their own judgment. If you think the addition of a second means little to your life, well, if you're watching this video, you're wrong, because the entire internet and the information speeding along it is governed by a time protocol that is in turn tied to a series of atomic clocks. Since leap seconds cannot be predicted, they must be inputted manually, meaning that they must be coded by individual people with individual flaws who might make a mistake, to say nothing of the toil and busywork involved. An addition of a leap second in 2012 caused Reddit to temporarily shut down. The leap second affects everything from the stock market to air traffic control to the electrical grid. Imagine if one were decreed during a particularly cold winter. If that wasn't enough, there is evidence that Earth's rotation may be, at least temporarily, speeding up. 2020 had 28 of the shortest days on record, and in June 2022, Earth hit a new speed record of 1.56 milliseconds. If this continues, the next leap second may have to be subtracted, something without precedent in the history of timekeeping, and for which the guardians of the grid have no plans. No one is entirely sure what is causing this, but some suggest a decay in Chandler's wobble. Given this, it's not surprising that tech giants like Amazon, Google, and Microsoft campaigned hard for the leap second's abolition. And on the 18th of November 2022, the General Conference on Weights and Measures resolved to eliminate it by 2035. Perhaps in 100 years, it may be replaced by a leap minute, but this is undecided as of now. If the leap second is maintained in some form, then according to meteorologist and astronomer Jean Maes, we would need to adjust the Gregorian calendar by about 7,200 AD. According to, well, me, so take it with a pinch of salt, if we abandon the leap second, then that adjustment will take place sometime around 9,400. The absence of the leap second would likely go unnoticed by all but the most obsessive of humanity, but would nonetheless be a landmark in our collective history. 100,000 years ago, we made fire, wore the skins of animals, created great art, and kept time by the sky. We still do all of those things, but if we lose the leap second, our last tenuous link to the timekeepers of the sky will be forever gone.